Hi class, so this is our last lecture in chapter 14, acids and bases. And this is going to be on chapter 14.7, which has to do with titrations. And we're going to cover worksheets 19 and 20. And 19 is embedded in the PowerPoint presentation that I'm going to go over. So you might want to have 19 and 20 handy so that you can take notes on them. And on worksheet 20, we're going to do 4 out of the 8 problems, I think. So we're going to do about half of them because there are several related. And so let's get started. So I'm going to share my screen, share the desktop. And here's the PowerPoint. So chapter 14.7 on acid-base titrations. So the first thing we're going to look at are titration curves. This is a plot of the titration of the concentration of the titrant. I'll explain what the titrant is versus the pH. So if we start with an acid, the pH is going to be low. And as you do the titration, which is a reaction with a base, the pH will increase. So that's what the curve looks like. And if you started with a base, and titrated the base with an acid, the pH would start high and then go lower. So we'll talk about that. And then lastly, we'll learn and understand the process, but also the calculations associated with acid-base titrations. Let me get out of this for a second. I like to so that's not a distraction. Let me come back to the screen share. So what is a titration? So in a titration, you have an acid or a base of known amount, and that's usually a concentration, so it's a molarity. So titrations are, it's an analysis, a chemical analysis, where you react a known quantity with a substance of unknown quantity, determine the unknown. And so if you start with an acid of a known molarity, you can react that with a known or a quantity of an unknown base to determine the concentration of unknown base. I think the purpose of doing the titration will become more clear as we do go through the calculations, but also you're going to do titration in lab and also examine titration curves in lab. So this is probably a preview of what you're going to have in lab. So a couple things. The acid or the base of known amount that you start with, this is called the analyte. Let me get my handy little pin up here. So the substance of known amount, we would call that excuse me, it's not the analyte. It's called the titrant, titrant. And the substance that you're titrating here, this is what we're titrating to discover the concentration of. This is called the analyte. Okay, so the analyte is the unknown substance, and the titrant is the known substance. Now you have to, even the analyte, you have to know some information about the analyte. You have to measure a certain quantity of it. You have to know what the chemical is, because sometimes you have to know the molar mass. So you have to know what the identity of the chemical is. And then you have to measure, you don't know everything about it. So there's the concentration, typically you don't know. But you do know, if it's a solution, you know how much you're going to use. So for example, in a titration, we might say, we're going to take 10 milliliters of this unknown base solution, and we're going to titrate it with an acid that we know the exact concentration of, say 0.1 molar HCl, and we're going to react it with this base until the reaction is complete. So until we've added as much acid to the base so that it's totally reacted. And then from the amount of acid of known concentration that reacted with the unknown base, we can calculate the concentration of that unknown base. Like I said, when we do the calculations, I think it'll be more clear. So these reactions, or this titration, is determined from the stoichiometry. I referred to a chemical reaction. So titration involves a chemical reaction. So a balanced equation is really important. So if we react an acid with a base, we have these coefficients that determine the mole ratio of the acid and the base. Sometimes that, that is used in the calculation of the concentration of the unknown substance. An acid-base reaction produces a salt and water. Sometimes this is called a neutralization reaction because the salt, if it's a strong acid and a strong base, the salt is neutral. And so you come up with a neutral solution at the end. So the end of the reaction, when you stop, it's called the end point. That's when the exact amount of acid has been added to the quantity of the base to neutralize the base. So it's a neutral acid-base reaction, it's a neutralization reaction. The end point is when you've added a stoichiometric quantity of each of these. And sometimes it's also called the equivalence point because you've added an equivalent amount of acid to the base. We'll talk about that when we look at the titration curves. So how do you know when the reaction is complete? Well, use an indicator. So this is a chemical that changes color at the pH when the reaction is complete. If it's a strong acid and a strong base, the reaction will be complete when the pH is 7. That's neutrality. We talked about that before. Solution is neither acidic nor basic. However, if you do the reaction with a weak acid and a strong base, or vice versa, a strong acid and a weak base, then you're left with a salt that actually can be either an acid or a base. So that salt influences the pH at the endpoint. So if you start with a weak acid and a strong base, the salt is a conjugate base. So the endpoint is going to be a little bit on the basic side because the salt is a conjugate base. It's a weak base, but it's still a base. If you start with a weak base and a strong acid, the conjugate acid of the weak base is indeed an acid. And so the pH is going to be a little bit on the acidic side at the endpoint. So you have to pick an indicator that's appropriate for the chemical reaction that you're running. So this is an example of a titration curve of a strong acid with a strong base, perhaps hydrochloric acid. Remember we talked about strong acids before. There were 6 strong acids that you need to know. So we'll say HCl and a strong base. Our usual strong base that we use is sodium hydroxide. And so in this titration curve, the beginning of the titration is over here when you've added 0 bases. The x-axis indicates the amount of sodium hydroxide added to the acid. So you start with a given quantity of acid. Let's say we start with 10 mils of acid, but we don't know how strong it is. We're going to start with 10 mils of HCl. And what we're trying to determine is what's the molarity of the HCl. What we're going to add enough sodium hydroxide that has a molar concentration, say, of 0.10 molar. We know that exactly. And we're going to add the sodium hydroxide until we've neutralized this acid. And when we've neutralized the acid, the moles of sodium hydroxide are going to equal the moles of HCl And then we can divide those moles by 10 mils to get the concentration in molarity. Well, molarity is moles per liter, so we have to change the 10 mils into liters. But that's pretty easy to do. Okay, so that's what happens. One of the key points is knowing when the endpoint is reached. In the strong acid or strong base, the endpoint is reached when the pH is 7. So if you can measure the pH as you do the titration, and there are machines to do that called pH meters, you know when you've added enough base to reach pH 7. That's the end. Like I said previously in the previous slide, another way is to add an indicator that changes color at pH 7. And if you don't have a pH meter connected to your solution that you're titrating, then you can just add an indicator to it. And that indicator will change color when you reach pH 7. So that's, we're going to talk a little more about indicators later. So let's look at some regions of this titration curve. So region 1, oh, by the way, this is, you'll find this titration curve in worksheet 19. So if you have worksheet 19 handy, you probably want to start writing on it now, or else remember, come back to the lecture and make notes on it. So at region 1, that's the starting point. I already mentioned that. And at the starting point, it's the pH of the acid solution. So this would be 10 mils of this unknown acid has a pH of about 2.5. Region 2 is a region where we started adding base, but the solution is still acidic, which means we haven't neutralized all of the acid. So the region, and the pH doesn't change very much, but it does increase as the acid reacts with the added base. Region 3 is the point where we've reached the endpoint, and with one drop of base, the pH increases all the way up to the basic pH. The solution turns basic. So it'll go from acidic to basic extremely rapidly. And that's because at the endpoint, the solution is neutral. And in a neutral solution, remember when we looked at buffers before? If you have an unbuffered solution, if you add one drop of base into, say, pure water, the pH drastically increases. It'll go from 7 to 10 with one drop of base, depending on what the molarity of this base is. So at neutrality, you don't have any acid, you don't have any base. One drop of base really increases the pH. So 4 is the endpoint. And it's the endpoint because the pH is equal to 7. And like I said, you can figure out the volume of the endpoint. So what's the volume of the endpoint? That's really the information that we want to know. Just draw a vertical line down from here and you get the volume. So at pH 7, the volume of the NaOH added is what we want to use in our calculation to determine the molarity of HCl. So this would be the end. You can, in this particular curve, the chemist has continued adding base, and as you continue adding base, you see the alkaline, or the basic region of this pH curve. So a pH curve, or the titration curve of a strong base, if we started with the base instead of the acid, starting with a strong base, the pH would be way up here. The curve would be the opposite. It would go like this and come down. So let me, maybe I'll just draw you what the curve of a base titration. So this was titration of an unknown acid. If we did titration of an unknown base, it would look something like this. So the curve would come down, down, down like this. It goes down. pH, as we add acid to the base, the pH is going to go down. And then we hit the end point, it would drop like that, and then it would go like this as the solution becomes more and more acidic. just drop down as we keep adding acids. So this would be the basic region. Neutrality would be again be at pH 7. And then the acidic region, if we started with a base, we titrate it with an acid. So in this case, the base down here, the added base is the titrant. Remember that? It's the titrant. This is our known substance. And the pH of the acid, that's what we're measuring here. This is the pH of the acid. This is the analyte. So that's the pH of the acid. Okay, so let's go on and let's look at titration of a weak acid with a strong base. The curve looks very similar. The difference is there's a little curve here at the bottom. This slope goes up maybe a little steeper, maybe about the same. But one huge difference is that in the case of the weak acid, the endpoint is on the alkaline side. It's on the basic side. It's above pH 7, so it's not neutral anymore. And that's because the weak acid in titration, when we titrate with a weak acid, we produce a conjugate base. We do that also with a strong acid, but in the case of a weak acid, the conjugate base is a base that's stronger than water. So it's a conjugate base that has a pKb greater than water, or a Kb, an equilibrium constant, a base equal greater than water. So because the conjugate base of a weak acid is a stronger base than water, the pH of that at the endpoint is going to be a little bit above the pH of pure water. So our strong base, then we're going to react it with the strong base, which again is sodium hydroxide. So the sodium hydroxide is our titrant again. And our weak acid is our analyte. So that's our titrant. I'll abbreviate it. And we're measuring the pH change of our analyte solution. So I'll just use a big A for the analyte. And that's what the weak acid is. Remember, the weak acid is going to produce a conjugate base when this reaction is over. At the end of this, after the equilibrium point, well, let's look at these different regions. Again, this is worksheet 19. So region 1 is the starting point. So the pH here of the weak acid is a little bit higher than the pH of the strong acid. Makes sense. The weak acid doesn't produce as many hydronium ions. As we progress along the titration, start neutralizing that weak acid, we start producing this conjugate base. And the pH goes up a little bit. But when we're titrating a weak acid with a strong base, this region becomes a very specific region we talk about. This becomes a buffer region. This becomes a buffer. Because if you remember, a buffer is made out of a weak acid and its conjugate base. So this is the buffer region when we're doing a titration between a weak acid and a strong base. And if we remember, so we know that there's really steep vertical. This is the neutralization point, or the end point is here someplace. I'm going to draw a vertical line down here. And it's about 20 mils. So the strength of this weak acid is about the same as the, well, it's going to have a, doesn't produce as many hydronium ions, but the concentration is going to be the same. It took the same amount of base to neutralize that. The hydronium ions produced by that weak acid. So if you recall, when we talked about buffers, that the best buffer is a buffer that's made up of the same concentration of weak acid and conjugate base. So when the concentration of the weak acid is equal to the concentration of the conjugate base, you have the best buffer. And it turns out that the pKa of that buffer, or the pH of that buffer, is equal to the pKa of the acid. So we can figure out where that point is on this titration curve. If it takes 20 mils to get to the endpoint, that means 10 mils is halfway to the endpoint, where the concentration of weak acid to conjugate base is 1:1. So the concentration of the weak acid and conjugate base are the same. So the pH here, which looks to be about 4.7, is going to be equal to the pKa. So right there at the halfway point, pH equals the pKa of the weak acid. So this is how you could find the equilibrium constant of an acid if you didn't know it. You can just titrate it. And at halfway to the endpoint, the pH is equal to pKa. Okay, let's go on. The endpoint is here. And in this case, the endpoint is above 7 because that conjugate base is a stronger base than water. And then as we go on, we hit region 4. And region 4, in the case of a titration of a weak acid and strong base, is exactly the same as a region 4 in a strong acid, strong base titration. So there's no more acid left. All we have is a solution that contains base, some conjugate base, and salt, or the conjugate base, which is the salt, and water. Okay, so there's no acid left, so this is the strong basic region. And if we look at the two curves, this upper part, if I overlay them, here's the other curve. Wait, let's see, we go up. There's a strong acid, there's the upper curve. So the upper part of these curves are exactly the same. It's the lower part that changes. Okay, so this is just interesting. I wanted to show you what polyprotic acid. Remember we talked about acids that have more than one acidic proton. That's called a polyprotic acid. In this case, this titration curve shows a polyprotic acid that has two acidic hydrogens. So it have a formula something like H2A, we'll say. And so both of these hydrogens are acidic. So the first hydrogen, the titration of first hydrogen is shown here at this first inflection point, and the second hydrogen then comes off at a higher pH here. Remember that halfway, polyprotic acids generally are weak acids, like carbonic acid, H2CO3, like I don't know, hydrosulfuric acid, H2S, or like what else? Phosphoric acid is a triprotic acid, H3PO4. All those are weak acids. So this has a buffer region. If it's the first proton's a weak acid, the buffer region would be right here. So halfway to the endpoint, which looks like it's at 1 here, 1 mil maybe. So at half mil, you'd have a pKa of the weak acid. This doesn't exactly look like a weak acid though, because this just is a nice gradual slope up. So this might be something like H2SO4, where the first proton is a strong acid proton and the second one is a weak acid. The second proton is definitely weak acid, so the pKa of the second proton would be halfway, it would be, you go halfway between the equivalence points, because at this equivalence point you have the first conjugate base. This is the second conjugate base. And so that when that proton comes off, you have equal amounts of the second conjugate base and that first conjugate base at the halfway point. So that would be, again, halfway between the two equivalent points. In this case, it'd be about 1.5. So we'll go up here at 1.5 and go over and find out what pH that is. And that would be the pK, we call it, if it's pKa2. Because it's the second acidic hydrogen. So the first equivalence point and then second equivalence point. And that's it. So we're not going to say too much about polyprotic acids, but the pH of a solution of polyprotic acid is primarily due to the pH of the first hydrogen that comes off. Not both of them, because they remember the first one ionizes much more easily than the second one. Okay, so let's look at a problem, a titration problem. So this is a typical titration problem. Oh, this is a sample problem from out of your book. So it's like the example problems in your book. So I made a note here, look at example problems 1421 and 1422. And homework includes some of the problems like 1421. So this is a problem where it says if you're doing a titration and you want to determine what the pH is at a certain point along the titration curve. So that's what these example problems 1421 and 1422 are. So in this particular problem, it says that 10 mils of 0.2 molar NaOH is added to 50 mils of 0.1 molar HCl. What will be the pH of the resulting solution? Well, this is a strong acid and a strong base, so you have to know that. So the first thing you want to do is write the balanced equation. HCl plus NaOH yields H2O plus NaCl. Again, the stoichiometry is important, so we have 1 mole of HCl will react with 1 mole of NaOH. Secondly, we want to calculate the moles of NaOH and HCl, but we'll do NaOH first because that's what's given first here. So we have 10 mils of 0.2 molar NaOH. So we just multiplied the volume in liters times the molarity, and you get the moles of NaOH. Secondly, calculate the moles of acid. So that's the volume of the acid, 50 mils times the molarity of the acid, gives you the moles of HCl. And in this case, we have more HCl than NaOH. So that means that there's going to be excess HCl. So the HCl going to be left over. That means the solution will be acidic. But how acidic is what this problem is asking you to determine. What will be the pH of the resulting solution? So right now, because there's more moles of acid than base, we know that it's going to be acidic. So 0.02 moles of NaOH are going to neutralize 0.02 moles of HCl. So we have to subtract that. So we're going to take our acid, which starts off as 0.005 moles. We're going to subtract 0.002 moles from that because that's how much NaOH we've added, which is going to neutralize that much acid. We end up with 0.003 moles of excess acid. Lastly, we need to divide by the volume. But in this case, it's the total volume. So we've combined 10 mils of sodium hydroxide with 50 mils of HCl. So the total volume is 60 mils. So we're going to divide by 60 mils down here, which is in liters because we're molarity. So we have 0.003 moles divided by 0.060 liters, and we get 0.05 molar HCl. Well, I think we can calculate our pH from that. Remember, the pH is minus the log of the molar concentration of hydronium ion from the HCl. So we'll do that and we get 1.30 for our pH. That's our answer here. So if this was a titration, the question is, where would this lie on the titration curve? So here's a titration curve. It's going to be region, it's going to be 1? No, because we've already added some base. Is it region 2, 3, or 5? Well, because the pH is low, it's around 1, we're in the region 2 still. Okay, second problem. If 5 mils of 0.5 molar NaOH is added to 25 mils of 0.1 molar HCl, what will be the pH of the resulting solution? So it's the same strategy. We start with a balanced equation. We calculate the moles of NaOH. So we take 5 mils, convert it to liters, 0.005 liters times 0.5 molar NaOH gives 0.0025 moles of NaOH. Calculate the moles of acid. 0.025 liters of acid times 0.1 molar gives us 0.0025 moles of HCl. We look at those and we say, well, the moles of NaOH and the moles of HCl are the same. So this would be the neutralization point in this titration. This is where we've added just the exact amount of NaOH to neutralize the amount of acid that's present. So if you look at our reaction, what's left, so this is gone and this is gone because we have added the same amount. So what's left is H2O and NaCl. Sodium chloride, this is the conjugate base of the HCl, but we know that's an extremely weak base. It's a weaker base than water. So chloride is a weaker conjugate base than water. So the pH is going to be determined by the water. That's all that's left. So we know that the pH of water, so there's zero excess of acid and base. Lastly, only water remains. The volume of the water doesn't matter. But what we know that in water, the hydronium ion concentration is 1 times 10 to the minus 7. And so the pH is going to be 7. All right. So let's go to the last problem. Oh, where would this lie in the titration curve? pH of 7. Looks like it's going to be right here because this is a strong acid and a strong base. So that's the equivalence point. Lastly, if we have 125 mils of 0.1 molar NaOH is added to 50 mils of 0.1 molar HCl, what would be the pH at 25 degrees C? Well, 25 degrees C, it means that the equilibrium constants are usually given at 25 degrees C. So round your answer 2 decimal places. So first of all, we want to write a balanced equation. We always want to have that in front of us. Calculate the moles of NaOH. When we do that, we get 0.0125 moles of NaOH. Calculate the moles of acid, 0.005 moles of acid. So in this case, in our reaction, we have excess NaOH. I'll put excess up here. Excess NaOH. So the HCl is going to go away. And we're going to have a little bit excess NaOH. So how much excess? We can calculate that. It's 0.125 moles minus 0.005 moles gives us 0.0075 moles of excess space. So we can divide that by the combined volumes, which are 175 mils, which turns out to be 0.175 liters. So the concentration of our NaOH becomes 0.043 molar. So we can calculate our POH, which is minus the log of the concentration of hydroxide ion. So we have minus the log of 0.043, which is equal to 1.37, but that's the POH. So we have to take 14 minus the POH to get our pH, and our pH turns out to be 12.63. So where's that on our titration curve? Well, 12.63 is right up here. So we're in region 5 now because we've added excess base. So that's an example of the kind of problems you'll see in those sample problems and how to, what's going on in these different titration curves when you combine an acid and a base in a titration reaction. So the last problem is the kind of problem we're going to see on worksheet 20. Now what you want to do is, this is a stoichiometry problem. And there are no example problems like this in chapter 14.7. If you want to see example problems, you want to go to chapter 4.5, which is quantitative stoichiometry, I think, in chapter 4. Go back to chapter 4.5 and you can look at some sample problems that are like the ones we're going to work here. So in this particular problem, I like to kind of look at, you want to start, the starting point is with a certain quantity. So I say, I call this a mil to mole to mole molarity problem. So you have to read the problem to figure out, this is the concept map that I use, a unit map of the problem. But you have to read the problem first to figure this unit map. So it says, in an acid-base titration, 32.7 mils of 0.1 molar KOH is required to completely neutralize 50 mils of H3PO4. Calculate the molarity of the H3PO4. So the H3PO4 is the unknown. This is the analyte. Then we talked about the analytes and the titrants. So this is the analyte. And the titrant then is the KOH. This is the titrant. And so we want to start a calculation, calculating, that's not written very well, but we want to calculate the moles of titrant. But we can do that because we have the volume and the molarity, and we know if we multiply these together, we change the volume to liters, we multiply liters times molarity, and we get moles. So that's what this path means. We're going to start with the mils of the titrant. We're going to multiply times the concentration to get moles of titrant. Then we can convert to moles of analyte and calculate the molarity of the analyte. So in this path, this unit path, on the left side, we're dealing with the titrant. I'll put TITR for the titrant. And on the right side, we're dealing with the analyte. So if that helps, you can use it. If it doesn't help, you can just not use it. So let's go on. So we're going to start with the mils of titrant. The reason why we're doing that is because we can calculate the moles of titrant. So you want to look at the information in your word problem and figure out what quantity or what is given in the problem that I can use to calculate moles. Well, in this case, it's the volume and the concentration of the KOH. So that's where I'm going to start. So you want to have a balanced equation to see what the stoichiometry is, because this is a stoichiometry problem. And when we balance this equation, we see that it takes 3 moles of KOH to react with 1 mole of H3PO4. Now H3PO4 is a weak acid. So that means at the end point, we're going to have PO43 minus left over. And PO43 minus is a base that is stronger than water. So what does that mean? That means that the pH at the end point is going to be above 7. So let's calculate the amount of KOH in moles that completely reacted with the acid. So we'll take our 0.1 molar KOH, multiply it times the volume of KOH in liters, and we get 0.00327 moles of KOH. Next, we want to convert that into the moles of acid. Third step, calculate the moles of acid. So we'll take our moles of KOH, multiply it times our stoichiometry ratio of acid to KOH, which is 1 to 3. And we get 0.00109 moles of acid. Lastly, we want to calculate the molarity of the acid, so we can divide by the volume of acid that we titrated. When you calculate the molarity of acid, you're not combining these volumes anymore. Remember in the last problem, we combined the volumes. So don't combine the volumes, because we want to know the molarity of the acid in 50 mils, not the molarity of the acid in the combined solution. So we want to know the molarity of the acid in the 50 mils we started with. So we take 0.00109 moles of acid divided by 0.05 liters, and we get 0.0218 moles of molarity, I should say, of the acid. So that's a typical titration problem. I call this a mil to mole to mole to molarity titration problem. So we'll see one of these in our worksheet. We'll go on to worksheet 20 now. And as always, you can look at this slideshow over again. It's available on the Canvas website. And if you have any questions, you can check in at office hours. The next office hours are going to be Monday or Thursday, is when I have office hours. All right, so I'm going to end this PowerPoint. And I'm still doing screen share, and I have a screen share here that has, here we go, here's our worksheet 20. So I've done this a little differently. I filled out the worksheet, and I'm going to put this worksheet up on the website so it will be available on the worksheet page. It'll be labeled worksheet 20 answer key. What I want you to do is to work the problems that are similar to these that I've worked, but need to be solved. Okay, so you get some practice. So I've worked problems 1, 2, 3, and 7, and I think there's a total of 8. Let me see, there's a total of 8 problems. Yes, there's 8 problems. Okay. So I'll go through 1, 2, 3, and 7, and I want you to work the other ones that are not, and they're similar to 1, 2, 3, and 7. So you shouldn't have any trouble. Different problems, but you work them the same way. So in the first problem, how many liters of 0.1 molar HCl would be required to react completely with 5 grams of calcium hydroxide? So let's identify the analyte and the titrant. Well, in this case, probably the titrant is liquid. Titrant has to be liquid, but this turns out to be the unknown. And we're given a gram of a certain quantity of calcium hydroxide, which is a solid. So what you would do is you take 5 grams of calcium hydroxide, you'd add some water to it to dissolve it, and then you would titrate it with 0.1 molar HCl. Now the titrant is a substance that goes into diuret. So there isn't an unknown concentration here. Remember, the analyte is usually what's unknown. What we want to know is how many liters or milliliters, in this case it asks for liters, the need of HCl would be needed to react completely or neutralize 5 grams of this strong base. So the reaction is down here. Stoichiometry is 2 moles of HCl per 1 mole of calcium hydroxide. The molar masses are given here, and that's pretty typical. In this case, we will need to know the molar mass because we remember these problems require solving for moles. And knowing the molar mass of calcium hydroxide, we can calculate the number of moles from this quantity given of 5 grams. And so the strategy then is to go from grams of calcium hydroxide to moles of calcium hydroxide, convert that to moles of HCl, and then figure out how many liters of HCl that equals. So I call this a gram to mole to mole to liter problem. Okay, gram to mole to liters. Remember the last one we did was, I think it was mils to moles to moles to molarity. Okay, we'll see one of those. So this is how I classify the problem that we have, the titration problem. This is a gram per liter problem. So step one is to calculate the moles of calcium hydroxide from the grams given. So we divide by the molar mass, we get 0.0667 moles. Next, maybe I'll use a pen here just in case I want to draw something. So next, we calculate the moles of HCl. So we can convert the moles of calcium hydroxide using the stoichiometry of 2 moles HCl per 1 mole of calcium hydroxide. So the calcium hydroxide cancel out. We're left with moles of HCl. We come up with 0.133 moles of HCl. Next, we will calculate the liters of HCl. So if we know the moles of HCl and we know the concentration, which is 0.1 mole per liter, we divide by that concentration, we'll get the liters of HCl. And it turns out to be 1.33 liters of solution. So that's step 3. So that's, so I'm going to change the color of my pen. I'll do that one. So that's problem 1. Problem 2 is also 3 steps. But let's look at problem 2. So if 10 mils of nitric acid completely neutralized 25 mils of potassium hydroxide, calculate the molarity of the nitric acid. So this is a titration problem at 10 mils. So 10 mils of, we want to know the molarity of the nitric acid. So this is a mil to mole to mole to molar molarity problem. This is like the example problem in the slideshow. So in this case, the nitric acid is the analyte, because we don't know the concentration. And the KOH solution is the titrant. So I'll just put a big T there for the titrant. And so if you look at these, the quantity that we can calculate moles from is from the what's given for the potassium hydroxide. So 25 mils of potassium hydroxide that has a molarity of 0.351. So step 1 is to calculate the moles of KOH by multiplying 25 mils, converting 25 mils to liters. So we divide by 1,000 because there's 1 liter per 1,000 mils. And when we do that, the mils cancel. It gives us, converts the milliliters to liters. Oftentimes I just move the decimal place over. So when I see this, I know I'm going to have to use liters. So I'll move the decimal place over 3 places. 3 places. So I put a 0 in front of that and a dot 0.025. So I just plug in 0.025 liters instead of doing that conversion. But in a few of these problems, I put in that conversion so you don't forget it. Multiply that times 0.351 molar, which is moles per liter. Remember molarity. And again, this is back in chapter 4. Molarity is moles. I've been using molarity a lot, but I thought I might write it out, moles per liter. So when you multiply liters times moles per liter, you get moles. And our moles of KOH is 0.08775 moles. Next, step 2, we'll calculate the moles of HNO3. So remember in our pathway, this is the titrant side. Once we get moles of titrant, we have to convert it to moles of analyte. And our moles of analyte then, we multiply times the mole ratio of nitric acid to KOH. And our reaction, these are both, this is a monopartic acid, has 1 hydroxide ion. So it's a 1-to-1 mole ratio. I didn't write the reaction here. I should have written the reaction, but it's a 1-to-1 mole ratio. And so the moles of nitric acid is also 0.008775 moles. Then we're going to count the molarity. That's the last step. We're going to divide by the volume of nitric acid, which was 10 mils. So in this case, I just moved the decimal point over 3 places to the left to get 0.010 liters. So I take my 0.008775 moles divided by 0.010 liters, and I get 0.878 molar nitric acid. Now you could say, does that make sense? So that's a stronger molar solution than the KOH. Well, it took more milliliters of KOH to neutralize 10 mils of NaOH, of nitric acid. So we started with 10 mils of nitric acid. It took 25 mils of KOH. That means the strength of the KOH is less in the strength of the nitric acid. So this answer does make sense. Because the strength of the nitric acid, the concentration of the nitric acid turned out to be 0.878 molar. And the concentration of the KOH started off to be, or is, in this problem, 0.351 molar. So that works. Okay, problem 3. Let's go forward. Oops. I'm going to move this. I think I can move this up a little bit. Let's see if we can move it up. Yeah, there we go. Okay. Let me clear my drawings here. So problem 3, we're problem 3 now. It says, how many mils of a 0.321 molar HCl solution is required to neutralize 5 mils of 1.28 molar KOH solution? This is sort of like problem 1, but we're given, instead of giving grams of a substance to neutralize, we're giving a quantity of a liquid quantity here. So I call this a mil to mole to mole to mil problem. Remember in problem 1, it was a gram to mole to mole to mil problem. So this is a mil to mole to mole problem. All right, so we're given mils, and we're starting here with the mils of KOH. And how do we know to start with that many mils? Well, it says how many mils of 0.321 molar HCl, so we don't know that. So we're going to have to start here. And we know we start here because we can use the milliliters of 1.28 molar KOH to calculate the moles of KOH. So that's our first step. Calculate the moles of KOH. So 5 mils times 1 liter over 1,000 mils changes mils to liters, times 1.28 molar gives 0.0064 moles of KOH. Step 2, we're going to use our mole ratio. This is a very familiar reaction. So we know the mole ratio of HCl to KOH in this reaction is 1:1. So we take our moles of KOH times the mole ratio of HCl. 1 mole of HCl divided by 1 mole of KOH. And moles of KOH cancel. So we're left with moles of HCl, which turns out to be 0.0064. And then we'll calculate the mils of HCl by dividing by the molarity. So we have 0.0064 moles of HCl divided by the moles of HCl gives us 0.0199 liters. But the question said, how many milliliters are there? So we have to multiply times 1,000 milliliters per liter. We get 19.9 milliliters. So that's your answer for number 3. So now we're on to question 4. And what I've written for question 4 is that question 4 looks like problem 2 above. So if you look at question 4 and read it, it's a mil to mole to mole to molarity problem. So I'm going to let you do that one. So the strategy for solving this problem is just like the strategy above for question 2. Here's the balanced reactions. You have to pay attention to the stoichiometry. It turns out that I don't think you need the molar masses. So the molar masses are just there for extra information. You don't really need those in this problem. Question 5. Well, question 5 is a mil to mole to mole to molarity problem. Also, so that's the same as question 2 above. This is a different kind of titration. So we're not producing salt and water. We're producing salt and a different compound. I guess we're reacting aluminum chloride with silver acetate. You get a silver chloride, which is a precipitate, and aluminum acetate. So we're really worried about, consider the titration of aluminum chloride with silver acetate. With 20 mils of 0.5 molar silver acetate, which is here, is required to react with 8.2 mils of aluminum chloride. So both of these are aqueous solutions. What is the molarity of that solution? So it's a mil to mol to mol to molar problem. And the unknown is this silver chloride. So in all these problems, I want you to identify the titrant and analyte. So I'll let you figure that one out. I'm not going to tell you. So the last problem I'm going to do is problem 7 here. And if you analyze this problem, this is a mil to mol. Oh, I skipped problem 6. So you need to solve problem 6. It is the identical problem to problem 1 above. So that'll be easy one. Just go look at 1 above, and that's how you solve it. So problem 7, let's look at that one. I said this is a mil to mol to mol to gram problem. And so it says how many grams of calcium hydroxide, so that's why the endpoint is grams. How many grams calcium hydroxide are needed to react with 69.9 mils of 0.350 molar hydrochloric acid? So the reaction that this is referenced is up here. So it's for this reaction. Now, since we're dealing with grams, we are going to have to use the molar masses. And in this problem, we're worried about calcium hydroxide, so that's here. Here's our calcium hydroxide. And we're going to react it with hydrochloric acid, which is here. And the mole ratio, there's 2 moles of hydrochloric acid per 1 mole of calcium hydroxide. So the information we're going to need to use, we're going to have to use the molar mass of calcium hydroxide in here someplace, because it's dealing with grams of calcium hydroxide. We're going to have to use this mole ratio. So I set up this problem as a mil to mol to mol to gram problem because we have mil of, we know how many mils of 0.350 molar HCl is used. So we can use that to calculate moles of HCl. Remember, all of these problems, if you notice, are all stoichiometry problems. And the core of the problem is a mole to mole conversion. So whatever you're given, you have to be able to calculate the number of moles. You might remember that from your previous stoichiometry problem solving that you did. So let's look at number 1, calculate the moles of HCl. So we have 69.5 mils times 1 liter over 1,000 mils, or like I said before, move the decimal point 3 places. That's a quick way. You get 0.0695 liters times 0.350 molar HCl, and you get 0.0243 moles of HCl. Next, we want to calculate the moles of calcium hydroxide. So we'll take our 0.0243 moles of HCl times the mole ratio of calcium hydroxide to the mole ratio of our reaction. That's 1/2, and we get 0.0122 moles of calcium hydroxide. And lastly, we'll take our moles of calcium hydroxide and multiply times the molar mass of calcium hydroxide. That gives us 0.912 grams of calcium hydroxide. So that's the end of that problem. And problem 8, that's another one for you to solve. So you have 4 problems to solve. You have 4, 5, 6, and 8 to do. And I'm going to put, like I said, I'll put this worksheet up there, the answer key, so you can use that as a reference for solving the problem. Problem 8 is the same as problem 7, the one just above it. So it's a mils to moles to moles to gram problem. So that's it. So let me stop my screen share. Let me start my video. And that's the end of chapter 14. So the next chapter is going to be 15. If you have any questions, like I said previously, just check in at office hours on Monday or Thursday. So take care. See you later. Bye.